So I'm really delighted to welcome Ian Cash from the International Electric Company, which doesn't sort of say exactly what the company does, to give us a talk on solar cells in space, which I'm all in favour of, and I'm waiting to be even more convinced. Thank you very much for coming.
Well, thank you for the welcome. Very pleased to be here, and very happy to be talking about space-based solar power and the CASSIOPeiA solar power satellite in particular. So we're part of the Space Energy Initiative, and we've currently got about 82 members. Shown there isn't all of them. There's about 66 down there, but you'll see IECL is another way of saying International Electric Company. And there's another company as well, which is leading the Space Energy Initiative, and this is Space Solar. And this is a recently spun out company which is a for-profit company and can take investment funding and develop the program for space-based solar power in the UK. So CASSIOPeiA, it does actually stand for something. Constant aperture, solid state, integrated orbital phased array. You'll probably all be familiar with the CASSIOPeiA constellation. Well, just off to one side of that is something you can't see with the naked eye, and that's the CASSIOPeiA A supernova remnant. That's a recent picture from James Webb, and this is the brightest source of microwaves in the night sky, and we're hoping to change that. So the first known reference to space-based solar power was in a 1941 short story by Isaac Asimov. And since then, there have been other stories as well. I'd say these books are fantastic. And by that, I mean that you're probably not going to learn a great deal about space-based solar power, but they are enjoyable reads. More recently, I can strongly recommend, if anyone's into hard science fiction, this trilogy by Daniel Suarez, and we don't know what the third one is going to be yet, but this does present a very plausible pathway to humanity becoming a spacefaring civilization, and space-based solar power playing a major part in that. This person probably needs no introduction, and this is where I might be making myself unpopular, because that's the Wardenclyffe Tower and Nikola Tesla. And unfortunately, it was a bit of a folly. Tesla didn't really understand electromagnetic propagation. He seemed to think that you could pump the Earth and generate these longitudinal waves, which was nothing of the sort. And he didn't really listen to the likes of Marconi and the works of James Clerk Maxwell. The actual first technical concept was presented in 1968 by Dr. Peter Glaser, and he is the true founder of space-based solar power. And working with his colleague, Bill Brown, together they presented a realistic concept which was taken forward by the NASA and the Department of Energy in the US. And this led to a 4-year study, which is probably remains the most detailed study of space-based solar power to this date. This is also an international collaboration. There are a number of groups around the world who are working on this, and we do talk to each other. So this was the recently formed committee. This was actually our second meeting in late March, and some of the main people who take part. And some other people also joined in remotely, including second from the top right, top left there. And someone I do want to point out is Martin Soltau, who's the co-chair of, co-CEO of Space Solar, and he was until recently the co-chair of the Space Energy Initiative, and has done a lot of work with making this a UK-based effort. But before I move on, there does seem to be something wrong with this image, that it seems to be lacking a lot of age and gender diversity, and that's something we would like to change. So, you know, I'm looking around the room now, and I'm hoping that perhaps that this is something which we can put right. So I thought I'd get this out of the way first because lots of people who know a little about space-based solar power often have strong objections to it. So this is a common one that I come across all the time, that it's not about delivering energy, it's about vaporizing targets. And I get this from RF engineers in particular who think that we don't follow the inverse square law, and over 36,000 kilometers, the level of power received is going to be minuscule and worthless. And this is another one as well, often by right-thinking people who are concerned about global warming, but think that we're going to be adding to the problem rather than to the solution. And lastly, this is the most common objection that, well, everyone knows that wind and terrestrial solar are cheap. Why do we go to the effort of going into space? So firstly, to try and answer, firstly, the safety and efficacy, we want to use frequencies which get through the atmosphere. Other groups are looking at using lasers, but they can be stopped by a passing cloud. And the whole point is that we want a form of solar power which is predictable, continuous, ideally, and dispatchable, and even exportable. And that means we're restricted to using frequencies somewhere between about 3 and 12 centimeters in wavelength, which is just to the left of that satellite dish in the picture. And because these are the frequencies we want to use, which are relatively long wavelengths, it means that the apertures and the size of the satellites themselves have to be very, very large. That means also that they can gather a lot of sunlight power, and the amount of power delivered will also be very large. But the area where it's delivered into is also very large, so it's at a relatively safe intensity on the ground, about a quarter of that of sunlight. And lastly, this same physics which limits the concentration of this power also works for us. We can basically have a beam collection efficiency approaching 100% if we make the apertures large enough. And as far as the objections from RF engineers, they love to use their Friese equation. But if they only took the time to actually put in the apertures we're suggesting are necessary, and the wavelengths and distances that we're intending to use, they would find that rather than minuscule power being delivered, they'd actually get 200 or 300% received over what is actually transmitted. And that should be a hint that their Friese equation is not applicable with the kind of aperture sizes that we need. So the other aspect is, are we going to cook the Earth? So first of all, I just want to talk about waste heat and trying to put it in perspective. So you can see 3 examples here. We have a thermal power plant, which could be coal, gas, fission, or even a future fusion plant. And most of the best thermal plants achieve around about 60% efficiency, which means for every gigawatt hour of electrical energy produced, you're going to be releasing about 650 megawatt hours into the local environment, either into a watercourse or directly into the atmosphere as water vapor. And terrestrial solar farms, we tend to think of them as benign, and in many ways they are, but they do tend, the best solar farms tend to be in dry desert regions, and there's an opportunity here to change the albedo in the local environment. The best solar cells currently in use are going to be somewhere around 30% efficient. Well, say currently in use, we're not actually there with solar cells in the field. So for every gigawatt hour of electricity produced, we're going to be releasing about 2.3 gigawatt hours into the environment. If we compare that with a large rectenna for space-based solar power, then we've already demonstrated in the mid-70s that we can do this conversion from microwaves to electrical power extremely efficiently. And I actually have an example which can be shared around the room later, which is just at the front of the stage here, of such a rectenna element. And indeed, this one was about 91% efficient. So in the case of space solar power, it's actually got the least waste heat released. But all of this is really just a distraction because the actual waste heat is minuscule compared to the true cause of global warming. And here, the Earth's disk intercepts about 174,000 terawatts of continuous power from the sun. Some of that gets reflected by clouds and reflected straight off the Earth's surface. Some of it gets thermalized, so it gets absorbed by the Earth and then later released. And when it's thermalized, that's the point where it gets trapped by greenhouse gases. Now, since pre-industrial days, we've increased the CO2 content in the atmosphere from 280 parts per million to around about 420 parts per million, which is a 50% increase. That took some doing, but it's humanity which has achieved that. And the point of this is that rather than worrying about the waste heat, we currently have about a 400 terawatt imbalance of power being absorbed by the Earth. And in perspective, whole of humanity currently consumes about 19 terawatts of continuous power, or averaged over a year. So in terms of energy, it's 19 terawatt years. 84% of that is fossil fuels. So 16 terawatts of fossil fuel power and a predicted requirement by 2050 of nearly 30 terawatts means that every terawatt of fossil power is responsible for 25 times, every gigawatt of fossil power is responsible for this 25 times imbalance. And every terawatt of fossil power replaced, there's a 24 times benefit in doing that with renewable green energy. But it's got to be the kind of renewable energy which can replace fossil plants. Just to let you know that within the Space Energy Initiative, we do have an environmental working group. This is a document which shows we actually have already done some preliminary estimates of our CO2 footprint, and this is for the entirety of a commercial gigawatt scale program. We've also looked at siting of rectennas and the possible impact they could have with ecosystems. So it's something we're taking very seriously. So if we've handled the challenges of space weapons and overheating of the Earth and the inverse square law, there's still this big one of will it ever compete economically with wind and terrestrial solar. So this is something I've just picked up recently from LinkedIn, talking about the duck curve, which is a measure of energy demand throughout the day. And you can see that rather than being a duck curve now, it tends to have turned into a canyon. So are terrestrial renewables cheap? Well, yes, they can be incredibly cheap. In fact, the price of power produced by terrestrial renewables, particularly solar, at certain times of day can go negative. And this is a barrier to more renewable energy companies entering into the market. You know, they can't have a business where they have to pay you to use their power. So the point I'm trying to make is that simple comparisons of levelized cost of energy, which don't take into account the time and of when this energy is produced, don't really represent the value of the energy. And the most valuable energy sources are those which are dispatchable, where you can have as much power as you need, when you need it, and hopefully where you need it. This is a recent report which has come out completely independent of the SEI and the UK efforts. And they've looked at space solar power in comparison with renewables with storage. And they're saying that there's a potential here for space solar power actually to be the cheapest form of energy. And one quote I've just picked out here was very beneficial for CASSIOPeiA. Anyone who knows a little bit about space solar power may be aware that Elon Musk is certainly not a fan. He's certainly not a proponent. But the only objection I'm aware that he's raised is this conversion from solar photons to DC power on the satellite, then converting to microwave photons and beaming them to the planet, then having to convert again back to electricity. And what's the conversion rate? This is the only argument, technical argument, that I'm aware that Elon Musk has raised. So I'd like to tackle that end on. So per square meter of intercepted sunlight, this is a rather good terrestrial panel. Might actually be superseded by now. But for every meter square of sunlight collected, you can deliver about 228 watts of electricity. Looking at space-based solar power, we have a little bit of a head start because there's actually more solar power available. The intensity is higher in space than it is on the ground. I'm not going to run through in detail here, but just to basically point out that we have gone through an efficiency chain. And potentially we could deliver about 255 watts for collecting 1 square meter of sunlight in space. But what we could do if we're using concentrated photovoltaics is do that with about 500 times less PV area than this panel has shown. We can do it with about 45 times less mass than that panel, and that's for the entire satellite. But the question has to be asked, is it all really worth it if we're just getting about 12% more power? Well, the answer to that is that it's not about the instantaneous power at noon on a good sunny day. It's about the average energy measured over a year. So this is real data for the UK, and I've done it for Morecambe as the most average place. Apologies to anyone who is from Morecambe. So the UK, typically, we get about 37 sun days in a year, and that is a measure of the intensity of sunlight gathered in 1 square meter on the ground, rather than sun days you get at the end of the week. And when you compare with what's available in a geostationary or geosynchronous orbit, we've actually got access to 497 sun days in a year, which is 13 times greater energy available. Looking at the most common way that terrestrial solar is implemented, you tend to have rows of east-west running panels, and they need to be spaced, particularly at far northern and far southern latitudes, so that during winter, when sunlight is coming in from a low angle, we're not shadowing one panel with a panel further down to the south. There are other ways of achieving this, and this is becoming popular. So whereas the example on the left maximizes the use of the panels, even though it's still coming in, the sunlight isn't hitting those panels face on early morning or late afternoon. But the one on the right is a way of having a shallow east-west tilt and completely carpeting areas of the ground. And this can maximize the energy production in a given area of land. And it's that which I'll use in the comparisons which are coming. But the question has to be asked, do we really want to be blanketing the surface of the Earth in an artificial surface, which is a possibility given the rate of energy usage which humanity is demanding? Looking at wind power, the point here is that people may assume that we already have storage, and in fact that simply isn't the case. When we have excess wind capacity, wind turbines are braked and this energy is wasted. And when we have too little, it's backed up by gas-fired power plants. So this graph showing wind in blue and gas in red, you can see that they're pretty much a mirror image of each other. And it could be completely impractical to try and use lithium-ion batteries to store excess energy when it's available over these multi-day periods. So the only potential really with wind power is to use electrochemical storage, such as electrolyzing hydrogen, storing hydrogen, or even ammonia. But the way that the wind can be so intermittent, it's not making good use of capital equipment. If we compare this with space solar, first of all, we've got about 10 times the surface electrical energy power density compared with wind. In fact, more than that in many cases. And it would be suitable both as being the storage mechanism or the alternative to storage for wind without curtailment, because when we don't need the space solar power, we can redirect that to places which do, rather than simply turning off the satellite. So going back to solar, we've got choices of whether we do seasonal storage or not. And this, again, is real data. This is looking at the worst case day. So whereas on a typical day, we'll get 33 sun hours from space in geostationary orbit, on this day in January 2009, we got 11 sun minutes. And just to show it wasn't a fluke, that's almost exactly 1 year later, that's what the UK looked like. And there wasn't going to be much solar power generated during that day. So without seasonal storage, we've got to cater for this worst case day. And without going through all the maths, it turns out we need something like 36 gigawatt hours of lithium-ion battery storage. And we need to severely overbuild our terrestrial PV. We need something like over 600 kilometers squared of PV. And that's 80,000 times more PV for the same energy produced of dispatchable or baseload power than using concentrated photovoltaics on CASSIOPeiA. With seasonal storage, then the amount of battery storage for the day-night cycle, that does reduce, but not by as large amount as you might expect. And comparing the costs there from the left side to the right side, you can see that the cost of those batteries are coming down from $6.3 billion to about $4.7 billion. That's more than the cost we're predicting for space solar power. And seasonal storage, I've already mentioned that you've got to store it electrochemically. You can't use batteries. And ammonia produced by electrolyzing hydrogen and combining with nitrogen from the atmosphere, that would appear to be a good first choice. One reason being that there's no carbon in ammonia. So we know that the UK isn't the sunniest of places, so another objection often raised is, well, why don't we just transmit the power from where it is sunny? This is a project which appears to be moving forward, taking baseload power from a site in Morocco, which is equipped with solar production, wind production, and a large number of batteries, and then running an undersea cable, high voltage DC cable, to Devon in the UK, which is about 3,800 kilometers long. Now, the interesting thing about this is the project cost has been estimated at around 22 billion US dollars, and the mean power to the UK would be about 3 gigawatts. If we expand that out, the problem is that HVDC cables are actually mature technology, and you're not going to get much cost saving when you go to higher levels of gigawatt power sent to the UK. In comparison, the cost of the program to get to the first commercial gigawatt scale of commercial power is very similar, but in this case it would be for 2 gigawatts of baseload power delivered. And subsequent to 10 gigawatts, this is where we're on a very steep learning curve, where the steepness of that curve is actually falling rapidly in terms of the cost of producing space solar power. Most of the effort and the cost spent is producing the first gigawatts. From then on, we could be down 1-2 billion per gigawatt, around to those levels. Now, we can argue about costs. A lot of that is opinion. We don't have the completed X-Links program, and we certainly don't have any completed space solar satellites. But we can look at this a different way. We can look at the resources required to produce this. And these undersea HVDC cables, they mass about 50 kilos per meter. And there's 4 of them in this case. We're looking about a total of 250,000 tons, a lot of that being copper. And we're not seeing the price of copper coming down recently, nor that of steel. Compare that again with CASSIOPeiA. Firstly, this is a bit facetious, but rather than transporting power over 3,800 kilometers, it's more like 38,000 kilometers. But the point of that is that we can actually export this power around about 6,000 kilometers surface radius with a satellite in geostationary orbit over Equatorial Guinea. So that's almost the entire hemisphere of the Earth below the satellite. And you can see that we need about 250 times less mined and refined resources to do this. The other biggest cost of space solar power can be broken down into the cost of space launch, and there's different ways of doing this. So I'm looking here on the left at the space launch system using shuttle-era technologies, and it's working out about $30,000 per kilo lifted into low Earth orbit. Compare this with the SpaceX Falcon Heavy, where potentially 3 of the 3 boosters are recovered. The upper stage is lost, but significantly reused, and we're looking at a cost of about $1,400 per kilo to LEO. The hardware itself can be extremely expensive if you're building one-of-a-kind satellites with a lot of manual labor required in that production. And at the end of the day, this is an instrument requiring nanometer precision. Again, comparing with SpaceX and the Starlink program, they've produced over 4,000 of these satellites now, and they're very much on a production line, and they're launched 60 at a time. Other things we could do to reduce costs. Can we minimize the size of the solar power satellite? Well, unfortunately, the answer is probably no, not really, because we're governed by diffraction physics of the microwave wavelengths we're using. These have to be large satellites. We're not going to do this with a CubeSat. Can we minimize the mass? Well, yes, and that's really the key to this. But rather than just thinking about the mass, what we actually need is the most bang for the buck. We need to maximize the power of the satellite for the mass that we need to launch to orbit. So looking at costs, this is just simply showing how costs have fallen over the years, but you can see that the SLS is actually slightly more expensive now than it was in 1995 in the shuttle era. Costs are falling with the likes of Falcon Heavy, and for anyone who watched the recent, not fully successful SpaceX launch of Starship, I think they will get there, particularly since they've got the expertise of launching Falcon 9. You know, there's a lot being invested in this. Potentially, we're looking at a fully reusable vehicle where the main cost of lifting to launch is the cost of the propellant. And it wouldn't be complete without including a British effort, reaction engines, and the air-breathing Sabre engine. And this is a derivative of the Skylon air-breathing spaceplane. If we ever get round to building this, or designing this and then building this, we could be looking at airliner-like launches, multiple times per day. So looking at concepts, here on the left, this is the Japanese concept. I introduced Koji Tanaka. Well, he was there on the screen earlier in the presentation. So here we've got a phased array which always faces the Earth, and we've got photovoltaics on both sides. But as this orbits around an equatorial orbit, you can see that sometimes it's going to be edge-on to the sun, and in that case, it's not going to be producing any power. This is another example from the US. This is Caltech, called various names. It started as the Space Solar Power Initiative. They've worked with Northrop Grumman and the Air Force research laboratories, and it's now got a very arachnid-type name, Spider, and in fact, one of the demos is called Arachnid. In here, it's very similar in some respects. It's not always facing the Earth. It's choosing a compromise angle between being sun-facing and Earth-facing. But the overall thing about this is that they can't deliver baseload power. And they're still not going to require significant battery storage if it's baseload or dispatchable power that is needed. Comparable, the amount of storage required to terrestrial solar. This is stepping back to the late 70s. This is the NASA Department of Energy reference system, 77 to 81. And this was originally aimed at a 5 gigawatt system. There was also a variation which gave 10 gigawatts delivered to Earth. And that achieved a specific power of nearly 100 kilowatts per ton. A current contender from the Chinese Academy of Space Technology, you can probably see as a derivative of this that we've still got electromechanical rotating joints to keep the phased array looking at Earth while the photovoltaics look at the sun. But we're wasting a lot of power just in the first 12 kilometers getting power from these panels to the phased array transmitter. In fact, about 300 megawatts in this case. And then we've got a further 38 or 36,000 kilometers to go. Should also point out that there was a variation using gallium arsenide cells and low level of concentration, around 2 suns, and that achieved nearly 150 kilowatts per ton delivered. This is an example of a sandwich panel concept, and this gets around the electromechanical rotating joints by twisting the sunlight instead. So this is a very good concept for space-based solar power. You can see that there's a concentration of about 3 suns on the PV side of this flat panel, and the other side is always facing the Earth. We've still got some mechanical steering, rotating these large primary reflectors, and that is a failure risk. That problem is solved with John Mankins, who you've also seen in the earlier slides, with his SPS alpha concept, where rather than having a single bearing failure risk, he's using multiple heliostatic reflectors to redirect sunlight throughout the orbit onto the PV side of this sandwich panel. And that's achieving slightly below 300 kilowatts per ton, 2 gigawatts for 7,500 tons typically. Should mention, I first looked at a solid state design which could deliver continuous power to the Earth from a small constellation. This I called Hesperus, which was simply highly elliptical solar power satellite, and it operated in what's called a Molniya 12-hour orbit. More recently, there's another company entered the realm of space solar power called Virtus Solis, and they have a system which is very similar in many respects, also in the same Molniya orbit. And by saying we need a small constellation rather than the multi-thousands required for Starlink, here we're talking about 3 satellites could deliver continuous baseload power to 2 locations at opposite longitudes in the Northern Hemisphere. But there's a challenge with it. Because they're basically both flat panels, you've got to choose this compromise angle from being sun pointing and being earth pointing, and the RF aperture is the most important here because we've got to be able to steer this beam, and there are limits to that. So what tends to happen is that we form a very shallow angle to the sun, and your whole panel is illuminated at about 0.3 suns. Compare that with the previous slide with a sandwich panel illuminated at 3 suns, 10 times greater intensity. So it's not good for specific power. So looking in more detail at sandwich panels, in very simple terms, photovoltaics on one side, we've got power management distribution in the middle, and the other side we've got a microwave transmitter. We want to basically push as much power as we can through this panel to maximize the specific power. And because they share the same structure, we've eliminated some of the mass. We haven't got the electromechanical rotated joints. But there are some downsides as well. We're limited to about 3 suns. And one of those limits is the fact that around the midnight period, this satellite is receiving direct sunlight on the wrong face, which is just heating the satellite. It's not actually generating more electricity for that. Sunlight tends to converge from a wide and variable angle, so it's not suitable for further concentration, so we can't use high concentration photovoltaics. And because it's Earth-facing, it has to remain Earth-facing with a very large and high inertia panel, we have to restrict this to working in circular orbits. So CASSIOPeiA took a sandwich panel, divided it in segments, and then pulled it out into a helix twisted 180 degrees. And in this case, we're always sun-facing. So the reflectors are fixed with respect to the rest of the satellite. And that diagram on the lower left is just attempting to show that it doesn't matter whereabouts you are in the orbit, it's always facing the sun. So we've got all the advantages of a sandwich panel. We've got further mass reduction because we haven't got the excess reflectors needed in this heliostatic concept. And we've got twice the aperture for mounting photovoltaics, here shown just using low concentration, wide area photovoltaics. Because the layers are edge onto the sun, and what's shown in orange is the phased array, which is actually mostly just vacuum, we're not receiving much direct sunlight. So estimates show that we can take this to about 4 suns concentration before we reach thermal limits. We're retaining collimation from these fixed reflectors, so we can then further concentrate sunlight to get the efficiency of HCPV. And because we're sun-facing, solid-state design, we haven't got these same momentum constraints. We can put this in almost any useful orbit. So more on CASSIOPeiA. It's a solid-state symmetrical concentrator version. This is the more mature concept, which will give 2 suns concentration coming from solar north and the same from solar south for 4 suns total. Here's the microscale concentration, or one example of. It won't necessarily be done by this manner, but the highest efficiency solar cells to date achieve about 47.2%, and these are multi-junction, high concentration photovoltaics, and that's exactly the kind of cell that we can make use of on CASSIOPeiA. The key to CASSIOPeiA is this novel helical phased array, which, rather than twisting things mechanically, we can steer the beam through a full 360 degrees, which hasn't been done by other types of phased array. And another thing I'll just point out is that to remain sun-facing, we do need 3-axis attitude control, but we can actually use solar photons to do this. We need a bit of excess area in addition to the reflectors as shown, but we don't need propellant for attitude control. We will need some propellant for station keeping. And to explain sun-facing, lots of people, some people struggle with this a little bit, and this short animation helps explain how we remain sun-facing as we orbit around the Earth. Shown here for an equatorial orbit, but the same principle applies in highly elliptical, highly inclined orbits of any nature. So here you can clearly see we just appear to be hanging in space, pointing at the sun, while the electronics steer the microwave beam around the satellite rather than moving anything mechanically. But what tends to confuse is when you then show this from Earth's perspective, and it then does look like the satellite is rotating when in fact it's just remaining pointing at the sun. We've got 3 variations of the concept, which are really just variations in the kind of system scale reflector we use, going from 4 sun in the most mature concept down to 1 sun with a quadrant planar reflector. The purpose of these is it gives us some flexibility. For any particular orbit, we can choose a variation either to give the highest specific power or to give the lowest mass of satellite. And by choosing 2 common frequencies, called ISM band frequencies, 2.45 gigahertz or 5.8 gigahertz, we've got roughly a 5-to-1 ratio in the power that can be delivered from any one orbit. Just showing there the specific powers. Not surprisingly, the 1 sun version has the lowest specific power, rising through 800 kilowatts. This is probably going to be the first variant which is actually produced. And in the mature concept, achieving perhaps 1 megawatt per ton, so higher than any of the other concepts I've shown. What orbits can we use? Well, we can start in low Earth orbit. The only particularly useful orbit I see is a polar sun-synchronous orbit, and we could deliver power during the 6 months of darkness in Antarctica or the Arctic, where the cost of energy is excruciating. Moving on from that, looking at a highly elliptical orbit, this is a strange one usually highly elliptical orbits have to be at a high inclination, but this was an orbit worked out by John E. Drame, which is a low inclination sun-synchronous highly elliptical orbit, and that would be very good for delivering power to equatorial and tropical regions. Here's the more conventional inclination for highly elliptical orbit, and for both of those 4-hour orbits, and the minimum power we could deliver is about 180 megawatts from these. And this is an 8-hour variant, very similar orbit, but obviously going to a higher apogee. And this turns out to be very good levelized cost of energy, even better than geosynchronous and geostationary orbits. And that's mostly down to the fact that the orbit is easier to reach, requiring less propellant to insert the orbit. We've also got better end-of-life options from this highly elliptical orbit. One of the key challenges we're going to have is how are we going to assemble these satellites? We're not going to have astronauts doing this. It is going to be robotically assembled. Probably not with free-flying robotics because of the propellant usage. We're going to more likely use a crawling robot, and that's one of the significant challenges that we need to solve before we actually build these satellites at any large scale. Zooming in on one of these modules, here it's showing low concentration PV. It's hard to show from a static image that PV is on both sides. And here you can more easily see that the gap between layers really is mostly vacuum. It's where the wire dipole antennas are, which allow us to steer the microwave beam. Here is another example using one option for high concentration photovoltaics, showing here Fresnel lenses and a small secondary glass optic over a very tiny millimeter scale photovoltaic chip. Worth pointing out that all photovoltaics used in satellites need to have a thin layer of cover glass, and that actually adds up to a significant mass of the PV panels, and that's for radiation protection. By moving to high concentration photovoltaics, that mass of glass shrinks enormously, lowering the total mass of the panels, increasing specific power. The efficiency of the cells increases as well. And because the glass is locally thicker over that cell, we've got better radiation protection. So here, to sum up, I believe that payload launch costs with the Falcon Heavy, they're already viable for space-based solar power. To maximize specific power, we think in a mature design, we can achieve 1 megawatt per ton, that's delivered power. We want to maximize the utilization. And here we've got 18 to 24 hours per day, potentially 365 days a year. We want to start smaller, and for reasonable commercial power, we think we can start at 180 megawatts or thereabouts, rather than immediately starting at gigawatts. And we want to have the benefits of mass production. So we've got a small number of mass-produced module types. And we can use this in a number of useful orbits, including these highly elliptical orbits. And that's the majority of this talk. Thank you.
Thank you very much. It's a fascinating story. I had no idea how far it has advanced. I'm sure we're going to get some questions. You actually answered the question that I hoped you'd address, and that is, I've heard others talk about near-Earth orbits, and it seems so much easier because you have some option to do some maintenance if you absolutely have to.
One of the challenges with a low Earth orbit, most low Earth orbits, you're going to spend about 40% of the orbit in Earth's shadow, which isn't particularly good for a solar power satellite, which is why most satellites in LEO have significant battery storage.
Right, okay. But I was interested, that's a flyer. Some hands going up. Let me start there where the microphone is, yeah.
Thank you for the great overview, Ian. I'm probably one of those who you mentioned struggle with the sun-facing satellite. The geostationary satellites face the Earth rather than Sun, whereas your large structure faces the Sun all the time. So how does this achieved? With propellant all the time, great large reaction wheels or something like this?
Yeah, so a communication satellite in geostationary orbit, you're quite correct that the body of that satellite, where all the antennas are mounted, that is Earth-facing. And a lot of the concepts actually use the gravity gradient of these very large structures to help keep it facing the Earth. But you'll also notice if you look at communication satellites, they tend to have solar wings. Now, they're always depicted as coming out horizontally, when in fact they are solar north and south of the orbital plane, if it's an equatorial orbit, as GEO is. And they rotate around to face the sun. So all the power that those panels produce has to get over a rotating joint. And that's the same as the early NASA concept, which is a significant challenge and a lot of mass needed for that. CASSIOPeiA, the whole body of the satellite faces the sun, so it's rotating once per year. So once you, simple Newton's laws, once you start something rotating, it will persist in that steady rotation unless acted on by other forces. There will be some microgravity and other perturbations which could stop that, which is why we need the attitude control to keep this sun pointing throughout the year. But rather than needing electromechanical rotating joints and massive high voltage distribution systems, we use this novel phased array to steer the microwave beam around the satellite instead to keep it pointing at the Earth.
What is the actual footprint of the beam at the Earth, so the receiving station, so to speak? And in order for that to be done efficiently, the phased array has got to be huge. So could you give us some idea of those two parameters, the footprint on the Earth and the size of the phased array? Thank you.
So I briefly showed the original NASA DOE concept. On the Earth, the footprint was a 3-kilometer disk near to the equator. It'll be stretched into more of an ellipse as it goes north or south of the equator. And the satellite dish was about 1 kilometer across. Now, point about that was delivering 5 gigawatts of power. And I think they were considering potentially a peak RF intensity on the ground of sort of a kilowatts per meter, which is a little on the high side. That's about the same as direct sunlight. Now we think that regulatory limit will be more like 1/4 that of sunlight. So for CASSIOPeiA in geostationary orbit, the main helical array is about 1.7 kilometers across. And if we're beaming power near to the equator, the minimum size of the rectenna will be something like 5 to 6 or even 7 kilometers across, depending on various things.
So can I go back to the near-Earth orbit? The problem with putting it into geostationary orbit is that this thing has got to be kilometers wide in order to be able to beam. If you go to 400 kilometers, then you can get started with something much smaller, can't you? I mean, isn't that attractive?
In fact, we would probably do some demonstration missions using low Earth orbit.
Yeah.
For commercial power, which is the goal,
Yeah.
in a low Earth orbit, what would happen is that we would need a massive constellation. And a simple indicator of that is the Starlink, where I think currently there's around 3,500 satellites currently on orbit, and this constellation is far from complete.
Yeah.
And
I'm just sort of scared that you have to make this thing kilometers scale before you can't make it smaller. If it's
we can make it a little smaller using the 4-hour highly elliptical
I
orbit.
can see a question.
Thank you.
Yeah, okay. Yes.
Do you foresee any impacts on communications on Earth in the ISM band, for instance?
Potentially, yes. It's something that has to be studied carefully. What I can say is that communications, particularly data communications, are moving ever upwards in frequency. And how many people here are worried about the 27 megahertz citizens band now being repurposed? Anyone use CB radio these days? You know,
Looking for a show of hands, yes.
Yeah. Personally, I've done some experiments with this, and I was thoroughly expecting that I wouldn't be able to use Wi-Fi in the vicinity, and pleasantly surprised that actually I could. 2.45 gigahertz Wi-Fi next to a continuous, non-modulated power beam, which was delivering around about that 230 watts per square meter.
We had a question on the right there.
Yeah, thank you. I really enjoyed your talk, actually. I thought it was really, really good, really interesting. A number of years ago now, 2007, the International Union of Radio Science published a report on space-based solar power. And they came up with a number of pros and cons. And it's great to see that you've addressed many of those here this evening. One of the things that they pointed out, and I wonder if you could comment on, was the transmission of the microwave beam through the ionosphere and down to the ground, and the fact that actually the ionosphere is not a smooth medium, it's a very, can be a very disrupted and irregular medium, which can lead to plasma instabilities and defocusing of the beam. I wonder if you could say what you've done to look at that.
Yeah, it's one thing I didn't actually include in the slide, but this is something which has been partially addressed by the JAXA and the Japanese movement. They are probably the world leading on retrodirective beam formation and steering. And the way this works is that the rectenna on the surface emits a low power pilot beam, which could be at similar frequencies or slightly different frequencies. And this is then received by the satellite, either in geostationary orbit or other orbits, across the entire array. And once it does that, it performs time reversal, if you like, or another word is phase conjugation, which redirects the power beam back down to the target. Now, with reference to the ionosphere, it's a very similar problem to what astronomers have with visible light astronomy, where they'll use a sodium laser to generate an artificial star at high altitude, and then use adaptive optics to adjust the mirror to overcome the distortions present by the atmosphere. So we've got a similar problem, but because the pilot beam and the power beam both pass through exactly the same regions, and hopefully with similar distortions, then because effectively we're doing time reversal, those distortions should be removed. This is something we plan on experimenting with at lower altitudes, ever-increasing altitudes.
So can I just pick up on, I wasn't quite sure where the centre of gravity of the talk would be, but what I'm taking on board is that the business of getting the solar cells up there and getting them wired up, the massively powerful microwave technology were not on your risk list. It's these, perhaps, it's these designs for optimizing capture of sunlight. Is that because you haven't got around to those problems yet, or they're regarded as low risk?
One surprising thing is that people assume that we're going to be working at the extreme limits of what's possible in terms of solid-state electronics. And in fact, we're not, because we're limited by the intensity of the sunlight hitting. If you just consider a sandwich panel with 3 suns, we're talking about 3 kilowatts per square meter. Now, when we look down at the individual chips controlling individual elements of a phased array, we're about at the 1 or 2 watts level, which is simple for electronics.
I mean, I understand that each element is working comfortably within limits, but you've got square kilometres of the things, and you've got to worry about failure and extremely reliable assembly, and that sort of feels okay.
Oh, no, it's one of the major things. I
Yes.
touched on it when it came
Yes.
to robotic assembly.
Yes.
Now, we want to make these modules as basically to click together like Lego. We want to make the process of assembly as simple as possible. And we want to do that without transferring power between modules, by minimizing the amount of electrical or wireless connections. We'd rather use wireless connections where they're needed for communications.
So when I worry about my inverter on my solar panels at home blowing up within 10 years, I shouldn't translate that logic to this thing.
Well, when we've got a kilometre which is at least, sorry, a satellite which is at least a kilometre across with meter scale modules in 2 dimensions, we've got about 1 million modules. So damage caused by radiation, by micrometeorites, will probably take out a small part of a module, not the complete module. But even if it did, it's going to have a graceful degradation is the term we'd like to use. But also, these modules are robotically assembled and can be robotically disassembled for maintenance and replacement.
Question on my left.
I was wondering if you could say a bit about the delivery of this, when things are expected to actually enter orbit, and also whether you're getting any support from the government.
Very good questions. I'll answer the second part first. Yes, we've had a lot of support and encouragement from the government, and we have received, I'd say, limited levels of funding at the moment, but the government is also talking to international partners. I think I'm safe to say that if you've read any of the large news on space-based solar power, you'll know that the UK is considering an alliance with Saudi Arabia. I can't speak much on that. Sorry, the first part of the question was? Delivery. Yes, so timescales, this will move at the speed of money. And if we get full funding, we're hoping that we'll have an early stage orbital demonstration within 3 to 5 years. We're hoping for commercial power delivery within the first 10 or 12 years. And from then it's ramping up. It's not game over once we've achieved the first satellite. We need to scale this up considerably.
Okay, there's an online question from Tom Jemison, which actually more or less picks up that question, which I think we've answered, the question about financial backing and what the company's next steps are. But so you're touting for softish money.
We have a number of possible funding sources. Some are more developed than others, but good to know, Tom Jemison, that you're online.
Well, can I ask a question?
Please, sorry.
What contributes mostly? Oh, first of all, fascinating talk, and if I weren't male, pale and stale, I would join your panel and come and work for you, I think. What's the main contribution to the mass of the satellite?
Historically, it has been the power distribution. Okay. Transporting electrical power in space is actually very difficult. The International Space Station doesn't use more than, I think it's about 120 volts peak, something of that nature. To transport power across large distances, we need to use high voltages. Any residual plasma is a potential massive short circuit, catastrophic short circuit of the system. So a lot of the mass of the power distribution is actually the insulation required. And also that insulation has to withstand micrometeorites.
Okay, thank you.
There's a question.
Hello, yeah, thanks very much. A fantastic and interesting talk. I was interested to know if, I'm not sure if I understood from what was earlier comments, if the phased array can be directed into multiple beams, could you therefore have many ground stations which are nearer to useful places rather than needing a lot of ground infrastructure? And the other question would be about the weather from the sun. I think we've just been hinted on there. Something coming from the sun could wipe this out, or could it not?
Yeah, so the second part of the question first. Satellites have to deal with a high radiation environment anyway. Less so in low Earth orbit than in geostationary orbit, where they'll spend almost their entire life in the outer Van Allen belt, which is a high radiation environment, not really suitable for astronauts. So there are ways of shielding against radiation. A lot of those ways of shielding add a lot of mass. So I think that the answer is that there's a lot of work needs working on to cover the normal expected background radiation. But also we've had a large number of space weather events where some satellites fail, some satellites survive. We don't think we're going to fare any worse than any other satellite. The highly elliptical orbits, in terms of lifetime radiation dose, we're actually in a more benign region than geostationary, particularly this 8-hour orbit. We skirt around the inner Van Allen belt to reduce the radiation flux. I've already mentioned on the photovoltaic side that we've got a greater thickness of glass radiation protection over the cells. And also we're expecting graceful degradation. You know, we've got around about 15 billion high concentration photovoltaic cells in the full-scale 2 gigawatt satellite. If some of these fail, then we're hardly going to notice. We'll know about it because there will be digital comms between all the modules to report their state of health. And the first part of the question again?
About directing the beam into many different destinations.
Yeah, that is certainly possible. You do need to have an even larger aperture if you want to create multiple beams and focus them into a similar 5 kilometre plus rectenna area. It's certainly easier if you have a flat panel phased array. It's going to be more challenging with a helical phased array such as CASSIOPeiA. But what you can do, because all this is electronically steered in the first place, we can do time division multiplex. We can move the beam within seconds or a few seconds from one place to another, which requires minimal, say, supercapacitor storage on the ground to iron out these interruptions.
Okay, I think we had a pretty good set of questions. It's generated a lot of really good.
Well, thank you very much. I appreciate the questions.
So I'm going to get to finish with a question you may not want to answer. If I were a betting man, would I put money on waiting for nuclear fusion on the ground, or this? You might not want to say publicly what you think, but both of them are quite risky, but this seems to have fewer sort of fundamental problems.
Yeah, the simple answer is that the science of space solar power uses nothing much beyond what was fully known in the late 1800s. So we haven't got any science, show-stopping science challenges to answer. We could be improved with the likes of material science, photovoltaics, and all the rest. With fusion energy, there are still significant challenges in...
Maybe to discuss in the bar. But
Sure. I would put my money on space solar power.
Quite right, yes. Okay, well, I'm sure you've done such a convincing job that we all believe that too, and that we can carry on the conversation in the bar. But thank you. That was a fantastic
Thank you.
talk.
Happy to be here. Thank you.